morning, everyone. Welcome and thanks for joining us today. My name's Adrian McNeil, and I'm a Director of Engineering at Cruise Automation. So at Cruise, I lead our engineering productivity team, and so we're responsible for building tools and infrastructure that supports the unique development workflows of building a self-driving car. If you're not familiar with Cruise, we're a self-driving car startup here in San Francisco. So we're backed by General Motors. We have also raised around $5 billion in additional funding from SoftBank and Honda. And our mission is to launch a fully driverless car. So if you're a passenger in one of our cars, there's no need for you to be responsible for the driving at all. You don't need to pay attention to the road. You can sit back, you can eat, you can read a book, watch a movie, get some work done, or sleep if you want. And our vehicles are powered by a wide variety of sensors. So we have cameras, LiDARs, several different types of radars, and also some powerful onboard compute. And our car needs to use all of these sensors to, first of all, it needs to make a 3D model of the world. So it needs to understand its environment. The second thing is it needs to make a plan for how it wants to navigate through this environment. And finally, it needs to turn this plan into steering, braking, acceleration commands. So this is the control stack. We're currently testing our vehicles here on the streets of San Francisco. And probably one of the best perks about working for Cruise is that we have this mobile app that employees can use to request rides in self-driving cars anywhere in the city. And testing in this complex urban environment provides really interesting, incredibly rich data that our cars and our engineers can learn from. What really excites me at Cruise is getting to work on tools and infrastructure that support the unique development workflows of our self-driving cars. So this actually is an example of one of our internal tools called WebViz, and it's a 3D web-based visualization tool that allows our engineers to understand any of our driving sensor data, see exactly what the car was thinking or seeing or doing at any point in time. There's different panels that they can turn on and off and different overlays to understand the internals of the AV stack. This talk is specifically about our simulation at Cruise, and simulation is incredibly important for building a self-driving car. It's one of the most important pillars, and it's also a super interesting challenge. So first of all, I'm going to talk a bit about what I mean by simulation for self-driving cars and why that's important. And then we're going to talk about the infrastructure that allows us to run all of these simulations at scale. And finally, I'm going to talk about the data pipeline and analytics that allow us to understand all of this data that we get from our simulations. So first of all, why is simulation important? As I mentioned, we test our cars on the streets of San Francisco, and it's a super challenging environment. We encounter pedestrians and cyclists, motorbikes, double parked cars, emergency vehicles, construction zones, far more frequently than we would if we were testing our cars, or when we test our cars in more suburban environments. And I'm going to talk a bit more about this photo in a minute. But first of all, I want to show you a couple of examples of the types of situations that we run into on a daily basis driving in San Francisco. So the way our cars are able to learn so quickly is that we do things like this. We take them in San Francisco into the middle of a school zone at rush hour. And this is the kind of situation that's difficult even for a human to navigate. So it gives us incredibly useful data about not only how our cars behave in this situation, but also, this is data that we can train from and learn from. We run into construction zones pretty frequently, so our car needs to be able to handle a sort of dynamically changing city environment. Double parked cars are, a very frequent occurrence in San Francisco. Even moving double parked cars in this case. And I guess you can't see here, but we're actually stopping for yeah. And sometimes when we're getting around double parked cars, we need to go into oncoming traffic. And we also need to understand when people are yielding for us and sort of expecting us to go. And these are all things that we got through fully autonomously. Finally, when we're making unprotected left turns, we need to know how to look for a gap in traffic and how to clear an intersection. So in the early days of Cruise, our development workflow mostly consisted of taking an example like this, one of these scenarios, and maybe something where we thought we could have done a better job at. One of our engineers would download this to their computer. They would be able to run through it locally, maybe make some code changes or introduce a new ML model. And then they would run it through the CI and unit tests. And once they thought that that was successful, they would deploy it on the road, and we would do that to gather additional data about how that code is performing in production. But this is a pretty inefficient workflow for two reasons. First of all, it takes a really long time to get feedback to our engineers. If every time we want to know how our driving is improving, we need to go out, deploy it to a car, drive around the road, and just sort of hope we run into more challenging situations like this. The second thing is, I guess most importantly, if an engineer is only working on a single scenario locally and they're making changes to that code, they may have made that one scenario significantly better, but they don't know if they've made 3 other scenarios slightly worse. So it's really important that our engineers can test their code across a wide variety of scenarios and sort of understand how our behavior is. I'll give you one more example. So this is starts with us making an unprotected left turn. We've got pedestrians that we need to yield to and look for a gap. And then we come across a construction zone. And we need to identify that this construction worker here is holding up the stop sign, that he's expecting us to wait. And then once he sort of starts waving us on, the car needs to navigate through the scene. And also needs to check that it's safe to cross these double yellow lines, and check that we're not worried about that other guy sort of running out in front of us. Why is he standing on the road? And this is another example of why simulation is really important, though, because while we come across construction zones every day in San Francisco. No two construction zones are the same. And it's really important that we can understand not only how our car behaves in scenarios that we have seen, but also ones that we haven't seen. And so with simulation, we can take something like this, and we can ask questions like, what would have happened if what if this human was standing more further out into the road? What if the cones were in a different place? What if the construction equipment was in a different place? So we can take one of these scenarios, and we can create many, potentially hundreds or thousands of variations on it. So why is simulation important? It allows us to validate our driving behavior across a large database of different examples before we go driving on the road. We get a faster feedback cycle for our engineers. And we can understand how our behavior changes as we vary one of those scenarios. I'm going to talk a little bit more about that later. So this brings us back to the intersection with the cable car. This photo was not actually taken in San Francisco. This is from our simulated driving environment known internally as the Matrix. And just like the Matrix, the car has no idea that it's inside. So we are simulating everything from the camera and LiDAR inputs using ray tracing. And then the car goes through its normal process of doing perception, planning, controls, and responding with steering and braking commands. And testing in a simulated environment like this allows us to reliably reproduce weird edge cases and scenarios that we haven't seen in the real world. In a simulated environment like this, we can control everything: pedestrians, cars, cable cars, even other cruise cars. And so simulation like this is one of the most important pillars of self-driving car development. Got a bit of work to do on our pedestrians walking. And this is just one type of example of simulation. So this is what's known as an end-to-end simulation, where we're simulating everything from our sensor input through to the steering and braking commands. But there's many other different types of simulations. So another example is a replay test, where we're taking actual sensor data that we've recorded from the real world, playing that back against the car stack, and then we can compare the results of this to our steering, and we can compare the results of what we detected to human-labeled ground truth data, and that allows us to score how well the car did at turning that sensor input into an accurate 3D model of its environment. Another example is a planning simulation. So in a planning simulation, we can construct an example like an intersection here. We have some pedestrians entering a crosswalk, the car's trying to make a left turn, and we can create an assertion such as that the car must yield to these pedestrians. And the key difference with this type of simulation is that we're not simulating sensor input here. We're simply giving the car a known state of the world, and then we're validating its behavior. And this is much cheaper to run if we want to do hundreds or thousands of variations. This is not an exhaustive list. There's many other different types of tests and simulations we run. So for example, we also do a lot of performance testing where we're running our car stack against real car compute hardware. And that way we can benchmark things like latency, CPU, memory, GPU use. So we have a huge number of these different scenarios. Every one of these scenarios, we might want to create hundreds or potentially thousands of different variations. Each of these tests that we run requires large runtime assets. So sometimes you might be using over 100 gigs of data that needs to be copied onto that worker, and that's things like binary assets, map tiles, ML models, recorded sensor data. And finally, these tests produce really detailed metrics and data. So a self-driving car simulation is much more than just a pass-fail result, just like driving well on the road is much more than just not crashing or just following the road rules. So our engineers really need to understand exactly how our car behaves in that simulation. It's critical that we pair the simulation with on-road driving for a couple reasons. First of all, we want to do on-road driving so that we can find new and unique situations. And the second one is we need to validate that our simulations accurately reflect the types of things that we're observing in the real world. So by combining this on-road driving in complex urban environments with simulation maximizes the result, that the rate at which our cars can learn. So that gives you sort of a brief understanding of what simulation means and why it's important. Next, I'm going to talk about the infrastructure that allows us to run these simulations at scale. Testing infrastructure at Cruise is running at massive scale. So every day we're running over 200,000 hours of simulations. We do this on a cluster of 30,000 instances with 5,000 GPUs. And you can think about this as 30,000 virtual cars driving around every day to validate our car's behavior. And just to put that number in perspective, Cruise has around 180 test vehicles registered with the state of California. So we're running over 100 times more cars in simulation than we do in the real world. We also produce nearly 1/3 of a petabyte a day of results from all of these simulations. If you asked me a year ago whether I thought we were running large-scale test infrastructure at Cruise, I would have said absolutely. But the use of simulation at Cruise is rapidly expanding as our engineers find new and unique ways to benefit from these simulations. And so our test infrastructure and the number of hours of compute that we've been running has grown by over 25 times in the past 12 months alone. So you can imagine this provides some pretty interesting scaling challenges. So we have really rapid scheduling of jobs. Sometimes jobs are changing state over 1,000 times per second. We need to deal with CPU, GPU resource availability, make sure we have quotas to support our demand. We need to balance our utilization and make sure that we don't have too many workers sitting idle or that we don't have jobs queuing. We need to distribute these job inputs. The 100 gigabytes of data needs to efficiently be moved to potentially thousands of machines quickly and efficiently. And finally, we need a data pipeline that allows us to make sense of all of this data that we generate from the simulations. We choose to run this in Google Cloud because it allows us to scale much faster than we can on our own physical infrastructure. So we do have some on-prem hardware that we use for testing on real car compute hardware. As I mentioned, that's great for performance benchmarking. But the vast majority of our compute runs in Google Cloud. One of the other main advantages is that Google supports these custom machine worker types. So we can choose exactly how many GPUs, how many CPU cores, and how much RAM we want for an instance. And this is really valuable when we're running different kinds of simulations. We get access to the latest generation GPUs and hardware, and this is really beneficial for the productivity of our engineers. And we're able to use the best-in-class managed services. So we take advantage of Spinnaker, PubSub, BigQuery, and Google Cloud Storage. I guess before we talk about our current architecture, it's helpful to think about where we've come from. So in 2016, Cruise was a pretty small company when it was acquired. Originally, it was about 40 employees. And we treated simulation as fundamentally part of CI. So we had a CI system that launched VMs and containers. And the CI system had a homogeneous worker pool. So we had to run all of our builds and tests on expensive GPU instances. We were also limited to 16 times parallelization, and that was due to some performance bottlenecks in the system. So ultimately, this resulted in engineers spending a lot of time waiting for simulations to run. We solved this by introducing a new tool called Hydra. And Hydra is a job scheduler. So it's called by CI or users requesting a job. Consists of a master and then various worker pools. And it can send jobs to these worker pools. On the worker, we use Docker to execute the job. And on the GPU workers, we're using NVIDIA Docker to provide access to that hardware. The Hydra master writes all of its job state and kind of results of these simulations into the Postgres database. And then, as often happens at early stage companies, we ended up with a whole bunch of dashboards and reporting tools which were talking directly to that database. As our load increased, though, it became clear that this architecture was not going to scale very well. So there were performance bottlenecks, especially in the database with locking and triggers. And it was clear that we needed to revise this. For anyone who's made change to a production system before, though, you'll know that it's much easier said than done. So any API that can be depended on will probably be depended on somewhere. And we had things like various reporting tools that were talking directly to these databases. We had triggers that we didn't want to interrupt. We wanted to switch over to the new system without any downtime. And we wanted to keep the worker API backwards compatible. So at the start of this year, we migrated to our new architecture. And Hydra 2 is a collection of individually scalable components. So we completely rewrote the Hydra master in Go. And that manages the scheduling, and it talks via the exact same API, backwards compatible API, to our workers. The scheduler has its own database, so it's using Cloud Spanner to track all of the current in-progress job state. And then from there, we replicate the job execution history, first of all, back to that reporting database that tools were depending on, and then also through PubSub to BigQuery, which is a much more scalable data warehouse. Hydra 2 was built to take advantage of all of the building blocks that we have available to us in GCP. So we're using things like Cloud Load Balancing, Kubernetes Engine, and Cloud Spanner to run the master. We're using Container Registry and Cloud Storage for storing our inputs. We have output data going into Cloud Storage, and then we're also using PubSub and BigQuery to manage our output data and our execution logs. I'm going to talk through each of these components, but we're going to start with the most interesting one, which is the worker pools. So our worker pools are made up of tens of thousands of instances. And our goal here is basically to recreate this, an entire room of servers that are running for our benefit from the comfort of our laptop. We do this using Google Compute Engine, which is a great product. It allows us to spin up a VM on demand. And as I mentioned, one of the great features about Compute Engine is that we can choose exactly what ratios of GPU, CPU, and RAM that we want. We're not limited to these kind of predefined instance sizes. And so Compute Engine has a feature called Manage Instance Groups, and this is similar to auto-scaling groups in AWS. And this allows you to create a template instance, and then you can scale up or down many hundreds of instances of the exact same size. Managed instance groups come in two flavors. So there's regional managed instance groups, and these are tied to a specific region, such as US West. And they automatically scale up instances and balance them across all of the zones. So in this example, we have US West as our region. There's an instance group in it. And then we're creating all of the instances in the 3 zones in US West. Unfortunately, when you use regional managed instance groups, it's very aggressive at making sure that you have balance of the number of instances across the different zones. So this is primarily designed for high availability workloads. If you're serving customer traffic, you want to have spare capacity. And make sure that if requests are coming in, you don't end up dropping one just because a zone went down. But for batch workloads, we don't actually care about that. We do care about, though, the fact that in this example, I guess, if we scale down a couple of instances in US West 1A, we don't want it to automatically just start killing random instances in US West C and start up new ones in A just to maintain that perfect balance. If we're halfway through a compute job, for example, we might be halfway through a 20 or 30-minute job, and we really don't want it to start killing random instances that are halfway through those jobs, just so that we can have perfect balance. So the other option that you have available are the zonal managed instance groups. And in a zonal managed instance group, it is only scaling independently within a single zone. So we can create one instance group for each zone, and we don't need to worry about perfectly balancing these workers. Another challenge that we have here is that these instance groups are limited to running 1,000 instances per group. And so if you talk to Google, it's possible to increase this limit a little bit, but not sufficient to run the tens of thousands of instances that we want. So the way we solved this is by implementing sharded managed instance groups. Basically, in each zone, we would create more than one managed instance group, and that allows us to scale above 1,000 workers in a single zone. This does make auto-scaling a bit more challenging. I'm going to talk a bit more about auto-scaling in a second. Each of these managed instance groups creates an instance from a single template. So if you want to run different types of workers like CPU and GPU workers, you need to create more than one instance group. At Cruise, we also have different types, different size instances for each one of these. So on our CPU workers, some jobs only need a few cores, and some jobs can take advantage of 96-core machines. Likewise, some of our GPU jobs only need one GPU, others can take advantage of multiple GPUs. And we obviously want to optimize the cost by not running workloads on machines that are over-provisioned for that job. So bringing this back to our diagram, we now have multiple availability zones in the region. Each of the availability zones has multiple instance types, and then each of these instance types has multiple managed instance groups within it. So at this point, we're starting to get quite a few managed instance groups up here, but there's one more thing that we need to consider. And the final picture of the piece of the puzzle is which region to select for the workload. So it's a little bit, it's actually a map of the world, believe it or not. And if you're thinking about where to run your compute workloads, there's several factors that you need to consider. So you need to obviously think about legal considerations if there's things like data privacy and where your data is being stored and processed. Latency requirements if your jobs need to talk to each other or talk to data in a different region. You want to co-locate your data in your compute, so you don't want all of your data stored in US West and then your compute happening in US East. And finally, not all regions are created equal. So if you're doing things like this, running thousands of GPUs, you really want to talk with your TAM or solutions architect and get a sense of which region is going to best support those workloads. In our case, the answer was multiple regions. So generally, when people are running in multiple regions, they're doing this, again, for high availability reasons. But in our case, we care more about having the flexibility that we can run our workloads in whichever region is easiest to get capacity. So we have pretty spiky workloads during the day. Sometimes an engineer will kick off a job and we might need thousands or more servers. And being able to create that in any region gives us great flexibility to be able to take advantage of quotas in multiple regions. Running in multiple regions, of course, isn't free, so there's additional cost and complexity with setting this up. You need to think about latency. For example, if you were running machine learning training, you would not want your workers talking across regions because that's going to be quite a lot of extra latency. But for simulation workloads, they're all running pretty independently, so that wasn't a problem for us. You do need to think carefully about where your data is located. As I mentioned, you don't want your data stored in West and your compute happening in East. So Google Cloud Storage has this great feature called multi-regional buckets. And when you create a multi-regional bucket, you choose a continent like the US, and then it automatically replicates your data across the different regions in that continent. So when you use a multi-regional bucket, you pay slightly more for the storage, but then it makes transfer within all of those regions free and fast. So bringing this back to our little diagram, we have at the top some multi-regional buckets. So we're using cloud storage and container registry for storing our data. We then have multiple regions. Each one of these regions has multiple availability zones. Each one of these availability zones has multiple worker types, and each one of these worker types has multiple instance groups associated with it. So we really end up with a huge number. You can see how it's easy to end up with dozens of managed instance groups doing this. To manage all of this, we're huge fans of Terraform. So Terraform allows us to easily define the infrastructure as code, and we can easily make updates and roll out changes to this. And Terraform modules are a really great way to build something like this because we can set up a template for this is what a particular instance group should look like, and then you can use that to compose what a zone should look like, and you can use that to compose what a region should look like, and you can sort of template and parameterize each one of those modules. When we run this many instance groups, we need to think carefully about how and where we are scaling. So a typical workday at Cruise starts with engineers submitting jobs in the early morning. It ramps up during the day. You notice there's a bit of a lull there over the lunch period. And then it tapers off a bit towards midnight. And we have some low priority jobs which can run overnight. But the majority of our engineers are getting their work done during the day, and we don't want engineers waiting on machines if we can all avoid it. So scaling like this is always a balance between two things. You have queue times and utilization. On the one hand, if we were to scale up too quickly, or if we were to scale down too slowly, then we would end up with excess capacity, and this would mean our utilization would be low. We'd be paying for servers that we don't need. On the other hand, if we were scale up too slowly, or we scale down too quickly, then we end up with jobs queuing, and that's not ideal either, because now we're paying for engineers who are waiting for these jobs to finish. So we need to be able to handle rapid changes in demand, but we also need to ensure that we're closely matching this demand curve, and that we're not over or under provisioning the number of servers we need. We have some unique aspects to managing this auto-scaling at Cruise. So we need to balance the scaling across multiple regions and zones and instance groups. In some cases, we want to prefer scaling in one region and only sort of start scaling up in another region if we can't get capacity there. We have different queues with different priorities. So if we have a low priority job, we might not want to scale up at all. We're just happy for it to kind of sit there in queue. And we also need to avoid interrupting long-running tasks when we're scaling down. And the default autoscaler that comes with GCP can target something like a stack driver metric. So you can target something like CPU use, or you can target your own custom metric like queue length. But unfortunately, when the default autoscaler scales down, it always picks a random instance to terminate. And when it does that, it only gives you 60 seconds notice that this instance is going to scale down. As I mentioned earlier, if we're halfway through a 20 or 30-minute simulation job, we really don't want to kill that instance just because it got unlucky. So to meet these needs, we built our own autoscaler, and I highly recommend this if you're not, if the stock autoscaler is not working for you. It's actually pretty easy to build with just a few GCP components. So we have here a cloud scheduler, which kicks off a cloud function every minute or so, and that cloud function is just a few hundred lines of JavaScript. So the cloud function is doing a couple of things. It reaches out to stack-driver, and it asks, first of all, for the demand. So how many jobs do we have running in progress? And how many jobs do we currently have queued? And then it looks at the supply side of things. How many workers do we currently have connected or that are currently scaling up? If it decides that we need to scale up additional capacity, it can do this really simply by just reaching out to the Instance Group Manager API there, and it can just say, please set the target size for this instance group to X. If it wants to scale down, it puts a message on a pub sub queue, and then whenever a worker is idle, it simply checks this queue to see if there's a shutdown message for that particular worker class. And the unlucky worker that drew the short straw just deregisters itself from the Instance Group Manager, and then it terminates gracefully. So this architecture allows us to ensure that we're only ever terminating workers that are idle. Another thing that we needed to consider when running this many instances is the networking. So we run all of our instances in a VPC, and this uses private IP addresses. And when you're using private IPs, it means that if you need to reach the outside internet, then you need to go through a NAT. Google has a product called CloudNAT, which went GA back in November. But when we set this up, CloudNAT was not available. So we actually had to manually create a whole bunch of NATs. And that meant we needed to create a NAT in every availability zone, basically, in every region. And some availability zones needed more than one NAT to handle the bandwidth throughput that we needed. And this works, but it's still infrastructure that we don't want to manage. So we're currently in the process of migrating to CloudNAT, and CloudNAT can automatically scale horizontally to support your demand. Also, if you're doing any communication with with managed Google services, you have to enable private Google access. So private Google access allows your machines that are running on private IP addresses to route directly to those services like BigQuery or GCS or Spanner. It allows you to route directly to those services without needing to go through your NAT. So it significantly reduces the bottleneck on your NAT. Private Google access is actually pretty complicated to set up if you're managing your own NAT instances. But if you're using CloudNAT, it's a checkbox when you set up your VPC. So check that box, and you will live a happy life. The final picture of the final piece of the picture here is storage. So as I mentioned, we're using Google Cloud Storage for storing inputs and output data. And we're using Google Container Registry to store our runtime container images. In Google Cloud Storage, we have things like application binaries, map tiles, machine learning models, and sensor data, all of these things that we need to run a simulation. We've gotten pretty amazing throughput from GCS. So this is our write throughput. On a typical day, we might be peaking at sort of a gigabyte per second. But we don't write nearly as much data as we read. So this is our read throughput. And you can see on a typical day, we're peaking at over 380 gigabytes per second of data. So that's over 3 terabit. And this is an example of where the cloud is super powerful. Because if we set out to build infrastructure like this ourselves, it would be incredibly challenging to manage reliably at that scale. and it would also not be value-add work for crews. Instead, we simply click a button in the console or write a few lines of Terraform, and we have this kind of capacity available to us instantly. We have a bunch of work coming down the pipeline for Hydra, so we're always making performance improvements to handle the increasing load. We're looking at task pipelining so that we can prefetch assets for the next job that we're about to run before we finish the current job. We're optimizing where we send jobs based on which workers already have resources cached. And we're A/B testing our worker updates so that we can make sure that workers are working successfully and that we haven't introduced any regressions in our work infrastructure before we start managing production load. So the last thing I'm going to talk about is our data analytics pipeline. If you recall from this previous slide, I mentioned that we're storing our output data in Google Cloud Storage, and then we ingest this into BigQuery. And like with Hydra, I think it's helpful to touch briefly on the architecture of where we came from before I talk about how we're using BigQuery. So in this diagram, you can see our simulation job scheduler. That's Hydra. And Hydra is pulling work from the build artifacts and from other simulation data that we need. And then the output data that it produces goes into our graph compute engine. And the graph compute engine allows engineers to run post-processing tasks. Like they might want to, for example, compare that output data against human-labeled ground truth data and create aggregations on that to score how well we did in that simulation. The post-processing data was then stored as Avro files in S3, and we chose Avro here for a couple reasons. First of all, it was just really easy to work with. Hydra already had the ability to save output files into S3. And secondly, we didn't need to worry about schemas. So our engineers could make changes to the AV code, or they can make changes to their post-processing steps, and that data would get written directly to Avro files, which they were then able to access without needing to go through any team or get approval to change their schemas. We have tools like Jupyter Notebooks and also custom analysis tooling, which could directly read these Avro files and then render them to create sorts of dashboards. But this architecture became pretty limiting once we started wanting to run more advanced analysis. Without a proper query engine here, we couldn't answer advanced queries without going back and editing those post-processing code. And this also created pretty significant memory use. Our front-end visualization tools needed to read these Avro files, and that did not scale well as the number of simulations increased. Finally, it's pretty time-consuming building this type of tooling if you're tying it specifically to the data format that you're using. There's many different ways we could have gone about solving this, but given that we were using Google Cloud, we decided to use BigQuery as the data warehouse. So we have an ETL pipeline here that's a simple ingestion service, and that's taking the data produced by our post-processing graph compute engine and it ingests this into BigQuery. We've had great success with BigQuery so far, so we're ingesting over 10 terabytes a day of data with no administration overhead to us. We can get this data into BigQuery within minutes of finishing a simulation, and we can query it within seconds. And the BigQuery SQL interface is accessible and supported by many different reporting tools, not just our in-house ones. Our engineers can access this data via the BigQuery console and UI. We also have things like Jupyter Notebooks and BI tools like Looker and Tableau that can access it. And we also have our own custom front-end analysis tooling. So the last thing I'm going to talk about today is a bit about this custom analysis tooling that we build. I'll give you an insight into the world of self-driving car development. So I'm going to walk through a complete example of a simulation and how we run that and how we understand the results. So here, bear with me here. We have a car trying to make an unprotected left turn, and the car needs to yield to these cars in the oncoming lane of traffic. So this is represented in pink. We also have what we call a region of interest, which is the dotted line that you see, and our car needs to clear this region of interest between that gap in traffic, between those two cars. What we're interested in this particular example is which gap our car chose to go through and what the gap size was, what the period of time was. And the gap size is the period of time between when car 1, the blue car, has left that region of interest and when car 2, the green car, entered that region of interest. Okay, so if you're still with me, keep that in mind and we'll move on to the next slide. This is an example of some of the custom visualization tooling that we built. So you remember we're looking at the gap size between the two cars as we're making an unprotected left turn. And in this particular example, we're comparing two factors. We're looking at how the speed of those oncoming cars and the distance between those oncoming cars affects the gap that we chose and the size of that gap. And you can see here that we're comparing a base branch and a feature branch. And then in the third box, you can see the delta between the base and feature branch. So engineers can easily identify with this particular commit how that impacted which gap we chose as a function of these two input parameters. Each one of these green squares here is actually a separate individual simulation. So that's running on Hydra, and that's generating probably a gigabyte of output data each. So you can see how we end up with these large-scale compute and data storage challenges once we start running these types of simulations. Another thing about this tool is that the engineers can actually click on one of these particular squares, and it gives them more information about that particular run. So we have a lot of ongoing work in the simulation tooling like this. We work closely with our AV engineering teams to understand what type of experiments they want to run and how we can best sort of understand and visualize those experiments. So thank you for joining today. Before I go, I want to leave you with 3 thoughts. So the first one, simulation for self-driving cars is a super interesting problem. It's a privilege to get to work on it. At Cruise, we're using the latest tools and infrastructure to build to test these cars at massive scale. So this includes things like Google Cloud and also in-house developed software. And finally, it takes a diverse range of skill sets to build self-driving cars. So we have not just machine learning engineers and robotics engineers, but back-end engineers, infrastructure engineers, 3D front-end engineers, data science. And we're hiring in San Francisco and Seattle if you're interested in working on these types of problems every day. So thank you.